Okay, here we go. So lots of negative values of r. So you really have to know where the angle is, and then you're going to be going across the pole into negative r territory for lots of this. That's what's pi making hard. So at theta equals 0, we start at -1. Where's that? So theta equals 0 points this way. So -1 would be here. Okay, and then what happens? As we go to pi over 6, we go from -1 to 1, right? This is pi over 6 right here. So pi over 6 is here, and by the time we get to pi over 6, we're at 1, right here. So how does it do that? Well, it gets in less and less negative to 0. So somewhere around pi over 12, it's going to hit 0. So it's going to get less negative to 0, and then more positive to 1, like this. All right, and then from pi over 6 to pi over 3, it goes back to -1, right? So from pi over 6 to pi over 3, it goes back to -1. So at pi over 3 is this one here. This is pi over 3. So -1 is here. So as I turn the next from here from pi over 6 to pi over 3, it's going to go back through the pole like this, and then out to -1 by the time we get to pi over 3. And then it's going to go from pi over 3 to pi over 2, it's going to head all the way down to -3. So pi over 2 is up, so -3 is down here. So then it's going to come like this. It takes a steady hand. There we go. Something like that. So now I'm at pi over 2, but I'm at -3. Pi over 2, -3. And then back to -1 in the next pi over 6. So that's here, 2 pi over 3. I'm going to be at -1, so I'll be right there. It's symmetric. Right there. And then, let's see, where am I? I'm right here at 2 pi over 3. So then at 5 pi over 6, it's going to be at 1. So 5 pi over 6 is here, and there's 1. And it's going to go through 0. So it's going to get less negative through 0. And then to 1, like this. Sorry, -1. That's where I'm at. I'm at 5 pi over 6. And 1. And now when it gets to pi, it's going to be back at -1. So pi is here. Pi goes this way. I'm going to be back here by the time I get to pi, -1. So it's going to make another little loop like this. Like that. Now I'm at pi. And -1. So in the next pi over 6, I'm back down at -3. So what is that? That is 4, nope, it's 7 pi over 6. And I'm at -3 when I'm at 7 pi over 6. So that is here, right there. -7 pi over 6 is this way. -3 would be over here, so it's going to come like this. Okay, and then the next thing I have is 4 pi over 3, -1. 4 pi over 3 is this radial line right here. -1 would be right there. And then back at, so next I'm at 3 pi over 2, 1. Oh, we like that. 3 pi over 2, 1. That's right there. Straight down, 1 unit. So, and then in between, it goes through the pole, right? It's going to go less negative to 0 and then increase to 1. So it's going to be like this. Through the pole. That. Almost done. And then it's going to go from 1 to -1 by the time it gets to 5 pi over 3. So 5 pi over 3 is this radial line right here. -1 is here. And then it's going to go out to -3 at 11 pi over 6. -3 is here. So it's going to go through the pole, 0, -1, -3. And where I'm at now, so then the last back to -1. So it's going to head back to -1 right here at 2 pi. So 2 pi is this way, -1 is here. So it's 3 leaves with 3 little leaves inside. And so it's it's really going by pi over 6 at a time. You really have to go by pi over 6 each time. Pi over 6, pi over 3, pi over 2, 2 pi over 3, 5 pi over 6, etc. So each section of this is like pi over 6. And you're going between -3, -1, and 1. Okay, any questions? That's a hard one, I know. But if you can do that, then you're in good shape. Okay, let's look at the web work real quick. Where's that? Okay, this one. This was had where is my pen? Oh. Where's my pen? Where's my pen? Where's my pen? Okay, I think for time's sake, we need to move on. So this define the equation of the tangent line. So I'm going to encourage you to check out the example from class Wednesday. We have, I think this may be spending too much time and then we won't finish. So we did an example on Wednesday like this. If we need to get with a TA or myself outside of class for help with this one, please do that. But I think we should move on. So what I want to talk about is area. Okay, got my pen back. So here's how area works. So now our functions are not y as a function of x, but they're r as a function of theta. So what is that? We know we get, something like this. Given a value of theta, the function tells us what the corresponding r is, and that plots a point, right? So for every theta, the formula, whatever it is, so r is a function of theta. The function tells us what r is for every theta, and when we plot all the points, we get some curve in the polar plane, right? So I'm just going to give 2 examples here. So there's theta 1 and theta 2. Okay, so before we get into, so we're going to talk about area concerning polar graphs. But before we do that, we got to just review one thing. So if you have a circle of radius, say capital R, and we cut a sector like this alpha, the question is, how long is this length right here? How long is that arc length? He wants r theta, or alpha, so alpha. So r alpha. Well, so the definition of alpha in radians is how many radius lengths are cut off by the angle. So alpha, that is the arc length, but measured in radius lengths. That's the definition of an angle, radian measure of an angle. It's the number of radius lengths that are cut off by the angle. That's what alpha is in radians. So then what's the arc length then in the units of the radius? So for instance, if I cut off 2 radius lengths, if I cut off 2 radius lengths with an angle, that means alpha equals 2. All right, if the radius is 30 meters, then what is the arc length? So if the radius is 30 meters and I cut off 2 radius lengths, then what is that arc length? 60, right? So if each radius is 30 and alpha equals 2, then that arc length will be 60 meters. 2 radius lengths of 30 meters each. So what does that mean our formula is for arc length? How many radius lengths we go around times the length of the radius. So he was right. So it's alpha r times alpha, or alpha times r is that arc length in the units of the radius. Alpha is the arc length in numbers of radius lengths. So if you multiply the number of radius lengths times how long each radius length is, you get the arc length. Should make sense. Okay, so we're going to need that little fact when we talk about area and polar coordinates. So what are we going to do? So rather than sum up lots of rectangles, now what are we going to? So we're going to think about a change in the angle and what kind of shape are we going to get when we do that. So if I'm interested in this area here from theta 1 to theta 2 and from the curve into the pole, right? So it's no longer below the curve to the x-axis, but it's from the curve inward to the pole. So this kind of wedge shape here is what we're after. And so what are our elements going to be? Not rectangles anymore. So if we look at a typical, so it's got to meet at the pole. So what are we going to be summing up now? Not rectangles. What are we going to be summing up? Well, what slices of what shape? Yeah, they're going to be like triangles, okay? So we're going to be, so remember all that stuff at the beginning of the course. We did the physics applications, a typical whatever, right? A typical amount of work, a typical pancake, and then add them all together. So now it's going to be a typical triangle. So we're going to do the area of a triangle. And what is the area of a triangle? 1/2 base times height. Okay, so the base was going to be this out here, right here. This is going to be our base, and we're going to use it as arc length. We're not going to do straight line. We're going to take a little bit of arc length. So what is that little arc length right there? Okay, so right, r varies as a function of theta. So what is the arc length? Well, alpha r. circular little piece of arc length is alpha r. What is this angle right here? It's going to be delta. It's a little bit of change in theta, right? So our angle is going to be delta theta, and our radius is going to be simply r. It's the distance out to the curve. So we're going to have, just like this, we're going to have delta theta, the angle times r. And that's going to serve as the base of our triangle. That's equal to b. Okay, and what is the height of the triangle? So if that's the base, that little arc length is the base, which we get from the arc length on a formula of a circle. What's the height of the triangle? What's the height? That should be easy. That's just r, right? So our typical little triangle of area is, this would be like a delta A. It's going to be 1/2 base times, sorry, base is the other one. Base, delta theta, times r, times height, r. So 1/2 base times height. So you got to imagine the height is this way, right? So this is the base here, and the height this is the height. So that's r. And then this is the base here, this way. So 1/2 base times height. And so then we make things small, and what do we get? dA, a little bit of polar area is 1/2 r squared d theta. So that's the area for a little bit of area, a little real skinny triangle. And then if we want the total area, that original area between the dotted lines and the curve there, and what do? Yeah, we're going to add up sum up all the little bits of area, all the typical areas from theta 1 to theta 2. And that's simply 1/2 r squared d theta. So that blue triangle, that really skinny blue triangle, we're adding them all up starting from theta 1 to theta 2. Right? And what happens? R varies between there. And so each one of these is different because r is different. R is variable, and so we need to add them all up separately for different r's. But that's how we get our total area formula in polar coordinates. So what you really have to keep track of is, what area are you getting? You're getting wedge-like areas that always are out from the pole. So from the pole out to the curve. From the pole out to the curve. It's not stacking things up and down to the x-axis anymore. The areas are from the pole out to the curve. So you get, what you end up getting is kind of wedge-shaped pieces that you're finding area of. So they have to really have that straight, because this is different. This is a different kind of mental image than our typical x and y rectangles, right? The vertical rectangles. Okay, so let's look at examples. Here we go. So let's look at this one. 5 cosine theta minus 2. I want to do 5 cosine theta minus 2. And let's practice sketching that. So the first thing we want to do is sketch that in rectangular coordinates. Okay, so where's the midline? -2. And where's the max and the min? So from -2, we go where? All right, so we're going to be at do it out here. So theta axis, our R axis. So down 2. So the minimum will be what? -7. Maximum will be +1. Positive. It's going to go up, what, 5 from -2. That's going to be 3, right? Isn't it going to be 3? And then what's the period going to be? 2 pi. That's easy. So pi over 2, pi, 3 pi over 2. This will be 2 pi here. Does cosine start at the min, the midline, or the max? It's at the max. Okay, so it's going to start at 3. And then head down to -2. And then at pi, it's going to be at -7. And then it's going to be back at -2. And then at 2 pi, it's going to be back at 3. Okay, so let's see how we do. So from 0 to pi over 2, it's going to go from 3 to what? 3 to -2, right? This is our pi over 2. So let's find out exactly what angle it crosses 0 and become R is 0. Let's find out what that angle is. So to find out the angle where it's 0, we want the radius to be 0, right? So we solve for cosine theta. Cosine theta is 2/5. So we're going to get in the first quadrant, the angle is going to be the arc cosine of 2/5. Wherever that is, let's get an approximation of that. 1.16. 1.16. So let's compare that to pi over 3. Okay, it's a little bit more. So this angle is a little bit more than pi over 3. Pi over 3 is 1.042. So a little bit past pi over 3 is where we're going to go through the pole. So let's account for that. So here's pi over 3. So it's going to be a little bit past pi over 3. Now let's just scrap that. Okay, so I just added this one here. Let's make it a different color. Does it show up? Let's try green. There we go. So the green line is this is the angle in the first quadrant where this thing is going to go through the pole, and then for angles greater than that, it's going to head down to -2. So we're going to start at 7, and then at pi over 2, it's going to be -2. Sorry, we're going to start at 3, +3, and we're going to up at -2. Okay, and so from 0 to the green, we imagine it decreasing to 0, right? It's at 0 at the green angle, this arc cosine of 2/5. So it's going to go from, just imagine it decreasing, 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 decreasing to 0. Something like that. And then the rest of the way from the green line to pi over 2, it's going to go to -2 here. something like that. So there's our first quadrant. And then by the time it gets to by the time it gets to pi, it's going to be -7. Where's that? So pi is this way. So where's -7? Over here. So it's going to increase from, or get more negative from -2 all the way to -7. So increasing, 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 like this. Okay, and then by the time it gets to 3 pi over 2, it's back at -2, so that's symmetric. So 3 pi over 2 is down, -2 is then here. So then it's going to get less and less negative, like this. Less negative, less negative, less negative, to -2, and then it's symmetrically going to go back from -2 to 3. By the time we get to 2 pi, it'll be back at 3 again. And then we could sketch, what angle will that be? It's going to be symmetric, so it'll be what? Negative theta equals negative. That's where it's going to hit 0 again. So here, so right there along there is where it's going to be at 0, and then increase from 0 to 3 again. Okay, so let's find, what do we want to find? We want to find the area of that inner loop. What's the area of the inner loop? Okay, area of the inner loop. So what are we going to do? We got to figure out, we know that it's going to be some theta 1 to some theta 2, 1/2 r squared d theta. So we just have to figure out what theta 1 is, what theta 2 is, and r is, and we've got it. So we want to think about what, sweeping counterclockwise, the way that we normally do. So what is that loop? That loop is for when r is positive, right? So one way we could do that is we could do the top half and multiply by 2. So then what are we looking at? Theta 1 would be 0. And then we imagine you've got thin triangular wedges with a vertex at the pole. You're adding those wedges. All those wedges have their vertex at the pole. So one typical wedge would be like this. So that's our typical element, right? Like that. We're going to add all those up. That is like a triangular shape, right? It comes to a point at the pole, and then there's a little teeny change in theta that gives you a little change on the curve, right? So it's a triangle. And so we want the first one at theta 0, and the last one where? The last one is going to be here at, what's that angle? That's our arc cosine of 2/5. Okay, so before we do the math, let's have the software do the graph that we sketched and see how we did on the sketch. This one. All right, let's see how we did on the sketch first of all. Amazing. Okay, So let's look at what we had. And so can we get a quick estimate of what we think that area will be, how much that area will be? Estimate what you think the area of the inner loop will be. Go, work it out together. Estimate what you think the area of the inner loop will be. Don't do no integrals. Estimation, right? Estimation. What do you think it will be? Okay, shout them out. What'd you come up with? What do you think? 7? 6 or 7? 6? 7? Other estimates? Did you get in the ballpark of 6 or 7? You did? Nodding? 6 back there in the corner? 6 or 7? Okay, cool. Let's see what it is. So we're going to do integral from 0 to cosine inverse of 2/5, 1/2. What's R? 2 cosine minus 5? 5 cosine minus 2? Is that right? Squared? All right, how do we do this one? Let's just review because this is on your final. Potential trig integral. So for this one, we can't do undoing the chain rule. To do undoing the chain rule, what? We need a sine theta outside of the square, right? If we had a sine theta outside the square, we could undo the chain rule. But in this case, we're going to have to multiply it out. So it's going to be 25 cosine squared minus 5 times 2 minus 20 cosine theta plus 4. And then how do we do cosine squared? How do you integrate cosine squared? Remember? Who remembers? Half angle formula? Easy. Super easy. Okay, we're gonna so that's just a roadmap to doing it by hand. That's a roadmap to doing it by hand. So we're gonna let the computer do it. So we want what? 0 to arctan of arc cosine of 2/5 of 1/2 5 cosine, I'll just use x, it's fine, minus 2 squared. Why aren't I getting a number? Oh, there it is. Okay. And why is it only 2.69? What am I setting up there? Only the top half, right? So this is just from 0 to the first quadrant, right? So we're going to take the whole thing times 2. Two times the integral from 0 to arc cosine 2/5 of that thing, 5.38. You guys were too big. Estimates were too big. What's wrong? Anyone come up with 5? Something closer to 5? Oh, you should spoke up. Some of your moment of glory. Okay. All right. So the inner loop, the area of the inner loop is about 5.38. 5.38. Okay. What about the whole thing? So what about the area of the whole thing? And so when we say that, what do we mean? Do we mean including the loop or not? So what are we going to get? Say if we integrated from 0 to 2 pi. What area would we get if we integrated from 0 to 2 pi? Well, it would do the top half of the loop, and then it would do the area of the outer loop, and then it would do the bottom half of the loop. So what area would we get if we did from 0 to 2 pi? Can you describe what that area, what that number would represent? So it's gonna, what it will do is it will find that, certainly it'll find this, find this 5.38, but then the rest of the way, will it find the area inside the bigger and outside the inner loop? So when it's tracing around the outside loop, it doesn't care about the inner loop, right? And the triangles are going to go from the pole. So if we go from 0 to 2 pi, (51.83), exactly what value is that? 51.83. What area is that finding? She said 2 of the small one, and then inside the outside one. 2 of the inner loops, and then the air also plus the area of the outer loop. Yeah, that's right. That's right. Because when it does the outer loop, it's going to give, and the parts where the angle is doing the outer loop, it's going to give this whole thing. So it's going to give the inner loop again. So it's going to be what I've just shaded in black plus the inner loop again. So now, how do I get this? So what I want now is the area inside of the outer loop and outside of the inner loop. Find that. So find the area outside of the inner loop, but still inside the outer loop. How would you find that? So you're going to take the 51.83, and what are you going to do? Subtract 5.38? Is that right? Is that right? Got to subtract it twice, right? I got to subtract it twice. So if I take 51.83 times 2 of these, that will give me the area outside the inner loop, but inside the outer loop. If I want the whole area, all of the area inside the outer loop, what would I do? If I want all the area inside the outer loop, I'm just going to subtract the inner loop once. I'm just going to subtract the inner loop once. 51.83 minus 1, 5.38. Okay, doesn't make sense. So when this thing is finding the area for all the part of the curve for the outer loop, it's shooting those triangles right through the inner loop and doesn't even know the inner loop exists. Right? It doesn't even know the inner loop exists. It's gonna be summing up all those thin triangles around, including all that area in the inner loop when it does that. Okay, so let's do it. What would be? So let's talk about now. Let's bring another curve into the mix here. So I want to bring in cosine of theta plus 1 along with this. Cosine of theta plus 1. Deleted it. That's good enough. Okay. So here's cosine theta plus 1 should be easy. We're just going to look from 0 to pi over 2. So the red one is cosine of theta plus 1, and the blue one is the one we just did, the 5 cosine minus 2. So in the first quadrant, there's 3 regions. R1, R2, and R3. So the first thing that's going to be important is the intersection. At what angle do these two curves intersect? Okay, so let's find that first. How are we going to find that? So we got 5 cosine theta minus 2 and cosine theta plus 1. Make sure that's right. Yep. So where do they intersect? Well, they intersect where r is the same, right? So where for the angle that they're the same distance from the pole, we need to find that angle. So if this is, r1 and this is r2, we're looking for the value of theta that gives r to be the same. So we can set the r values equal, right? We're going to set the r values equal. So 5 cosine theta minus 2 equals cosine theta plus 1. And so then 4 cosine theta equals 3. And cosine theta is 3/4. So it's the arc cosine of 3/4. So let's change that green. We had our angle lines there. I don't know where I put it. There they are. So we want now the cosine inverse of 3/4 instead of 2/5. And that goes right through the intersection point. Turn this one off. Okay, so we got that angle. It's going right through the intersection point. So we want to set up expressions to find the areas of R1, R2, and R3. Let's see. R3 is going to be different. So we'll do R1 and R2. So how are we going to find the area for R1? Can you set up an expression that will find the area of R1? What is R1? It's outside of the red and inside of the blue curve. Outside of the red and inside of the blue curve to the angle of intersection of the two, which we found to be the arc cosine of 3/4. How would you set up that expression to do that? In general, what will the structure of it be? The structure of what we set up, what will it be? Remember that polar areas are from the curve, a triangular wedge, all the way to the pole. From the curve all the way, triangular wedges all the way to the pole that you stack up radially, right? You stack them up, you sweep them out radially. So what will that be in general? How are we going to get that right there? Any volunteers? How are we going to do that? Yeah, nice and loud. So you want to subtract, are you going to subtract radii? So it's not subtracting radii, but we're going to actually subtract areas. Yeah, go ahead. Yeah. Uh-huh. But you got 2 different curves here, right? We want the in between. In between. Yeah.
So it's the inner. So it would be 1/2 5 cosine theta minus 2 from 0 to arc cosine 3/4.
Uh-huh.
1/2 5 cosine theta minus 2.
You see it's going to be the difference of areas? If we do the area for the blue curve, it's going to take all the area to the pole. Because that's how polar areas work. They're triangular wedges from the curve all the way to the pole. So if I do cosine inverse 3/4 of the blue one was our original one, right? 1/2 5 cosine theta minus 2 squared. That's going to find all the area from that blue curve all the way into the pole from 0 to the green line, from the x-axis to the green line. So then how are we going to get R1 out of that? I got to subtract a whole other area, right? What area am I going to subtract? Same bounds. I'm going to do 1/2, what? Cosine theta plus 1 squared d theta. So you got to find the outside area from the pole out to the blue, from the pole out to the blue curve, and then you're going to subtract from the pole out to the red curve, and that will give you R1. Same bounds, right? Same bounds. Don't pack up. We gotta do R2. What's that? We're looking for R1. Area of R1. Who asked that? So what does that have to do with R3? How are you seeing that? R2, right. Oh, well, no, but no. R1 is this right here. If I do the integral of the blue curve, it will be all the area from the blue curve to the pole. It'll be R1 plus R2. This first integral here will calculate R1 plus R2. Do you see that? That first integral in my expression is going to calculate the sum of R1 plus R2. Because it'll be all the area from the blue to the pole. Then if we just want R1, which I've shaded there in black, we've got to subtract out the wedge that's R2. Yeah? It goes to the intersection point. So a typical, how about I don't make this too confusing, but a typical slice for R1, if I integrate on that blue curve, this is what I'm going to be adding up, a bunch of these. Do you see? If I integrate the blue curve from 0 to the green line, I'm going to be adding up a bunch of those. So what's that going to give? That'll give the total area of what I've called R1 plus R2. Because these typical elements go all the way to the pole, all the way from the pole to the curve. So if I want what I called R1 that's outside of the red curve, I need to subtract R2. R2 is then all of the area from the pole. Here's a typical element for R2. And if I subtract all that typical element from 0 to the green line, when I subtract, I'm going to get R1. Do you see it? Okay, now, so what about if I just... I didn't say that quite right. Sorry. Because there's a little bit more. This is correct, but this is not exactly R1 plus R2. But it's all the area. So everything I said was right, except this is not R1 plus R2. Okay, this is not R1 plus R2 because R2 also includes that stuff on the left of the line. All right, so we're going to have to finish this later. All right, let me just, while you're quietly packing up, let me show you Blackboard here. No, don't talk. You can pack up. Please don't talk. On Blackboard, here we go. The first announcement has everything you need to know from here on out. So there'll be the last web work set will be due Monday at 7. Okay, that's after we'll have a review study session Monday from 2 to 4. That's an ECA 225. All right, so then after that review study session, the web work set will be up, and then after 7 p.m. Monday, you'll be able to see the answers to study. Okay, and then the final exam is Tuesday night, 7 p.m. in Neeb. Neeb is close to Coord over here. Or, yeah, this way. Somewhere close to Coord is Neeb 105, 7 p.m. If you go to Exam Prep and Homework Solutions, I've got 2 documents for you. Those 2 documents are together form a comprehensive study guide. Okay, the first one is what you're already familiar with, where you're doing your polar homework, the sketching. All of that is fair game except this page that says functions as series. That's not on there. But everything else is, okay? Taylor and Maclaurin, yes. Parametric, yes. And then polar, of course. Okay, then I made a new sheet for you that has a comprehensive list of topics and suggested practice problems. So what's on the final? Integration techniques, areas and volumes, physics applications, Taylor and Maclaurin, parametric and polar. Okay, suggested problems to study. So those 2 documents together form a comprehensive study guide. Okay? Make sure you disregard the functions as series on that first link. And so Monday 2 to 4, study practice session, then Monday night at 7, the last web work is due. Loud, nice and loud.